Hello, 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 everybody. So, welcome to Unit 6, the last unit of the year. It's crazy that we are here right now. All right, today we're going to talk about linear correlation. And I put the word linear in there myself. All right, so concept of correlation in general was developed by some dude. His name is Carl Pearson. Okay, cool dude. You can look him up. All right, and he came up with a statistic, and it's called the Pearson product moment correlation coefficient. Oh my goodness, that's a mouthful. Whew. You know, we also just call it the linear correlation coefficient, the linear correlation coefficient, and it's denoted with the letter R. All right, so we are going to calculate the Pearson product moment correlation coefficient, or the linear correlation coefficient, R, for the following data. All right, and it's when you have two sets of data and you're trying to find the correlation between the two. Now, let's back the train up. What does correlation mean? Correlation is just a fancy word that means a relationship between two variables. So we are trying to find out if there is some relationship between X and Y, the two variables. So how can we plot, figure that out? Well, why don't we plot the two on a graph like this, 1, 4, and then 1, 5, and 2, 8. And so on and so forth. 4, 15. Plot them on something called a scatter diagram or scatter plot. You've all done scatter plots in your life. So fast forward, what are we going to be doing over the next couple lessons? We're going to make a scatter plot, and then we're going to draw something called a regression line. A regression line is something that matches the pattern of the dots. Okay, and you're never going to have one line that goes through all the dots. The line might be slightly above some of the dots. It might be slightly below some of the dots. Points, they're not dots. They're data points. Sorry, use the correct terminology. They might be slightly above or below some of the data points, but it's a rough average. Now, just interesting fact, if you take all these x's and average them, you'll get x bar. If you take all these y values and average them, you'll get y bar. The coordinate x bar, comma y bar is called the centroid, and it will always fall on this best fit line, it's called. It's actually called a least squares regression line. We'll get there in one lecture. All right, but we're getting ahead of ourselves. First, let's plot these points as coordinates, draw the scatter plot, and let's find R. Now, if you are interested in finding R by hand, here's the definition formula. If you're interested in finding R by hand, here is the computational formula, as we've been giving all throughout. Now, what are these notes right here in Doc Piper handwriting? It basically says, I'm going to decipher this. R is like slope. Oof, that's disgusting right there. Let me erase that. R is like slope. Oh, that didn't work. It's like slope. All right, so if a line goes downhill, R is negative. And if the line goes uphill, R is positive. That's basically what number 1 says. I know it's Doc Piper handwriting, so you have to have trouble deciphering. All right. Number 2 says R is not affected by the y-axis. Throughout our lives, we are going to experience many graphs where lines look like they are going like this, or lines going like this, and guess what? They could be the exact same line. It just depends on if the y-axis is going up by, ones or by hundreds. Okay, we need to be educated consumers or educated people and not be fooled by the y-axis. So R is not fooled by the y-axis. And number 3 basically just says R is a sample statistic, and it's used to estimate, it looks like the letter P, but it's actually the Greek letter rho. Just like X bar is used to estimate mu, just like P hat is used to estimate P, the population proportion, R is a sample statistic used to estimate rho. All right, that's what number 3 says. All right, if you would like to calculate R by hand, you could use the definition formula, you could use the computational formula, and it looks like they are only one 1,000th off, 0.996, 0.997. If you would like to know how to do it on your calculator, that's what I'm going to show you right now. All right, so let's go to your calculators, go to stat, go to enter, put the data in X's in L1, the Y's in L2. That's step one. This is basic stuff right here. X is going L1, Y is going L2. This is what you all need to do one time and one time only. All right, hit second, then the number 0. And you need to arrow down all the way to the D's. You could just hit alpha D. I'm just going to do this for effect right now. We're already at C, so I'm just sticking with it. All right, we're almost at D's right now. Okay, once again, you could just hit alpha and then find the letter D and hit it and you'll go right to D's. That's much quicker, but I've already committed. All right, so I'm gonna go until I get to, I just passed it, diagnostic on. All right, so scroll down till you get to diagnostic on, hit enter, and then enter again, and it will just say done. What have you done to your calculators? Nothing. You have just enabled more memory to be used. But your TI-84s and 84 pluses and 84 CEs, they have so much memory, you're hardly using any of it. So basically, you're just allowing 2 more bits of code to be put in. Okay, that will never have to be done again. Your diagnostics are on until your batteries run out. All right, so you're going to go to stat now. You're going to go to calc. Until now, we've been using 1-bar stats this whole time, but look down this list. Does anything look like the equation of a line like the one I just drew? Yeah, step 4, lin reg, ax plus b. M is used for another feature in the calculator, so a is the slope, b is the y-intercept. So hit enter. Are the x's in L1? Yes. Are the y's in L2? Yes. There is no frequency, so go to calculate, hit enter, and a-blow. Now, what is all this mumbo jumbo? Well, it's y equals ax plus b. So notice this is a equals 3.12. That's the slope of the line that I just drew in red. B is 1.65. That's the y-intercept of the line that I just drew in red. And R is 0.997, basically, 0.9967, so 0.997. Let's go back and show you what I'm talking about. That means that this line that I just drew right here, this line, the equation of this line, and it's actually y prime, we'll get to that tomorrow, is 3.12. That was the slope, x plus 1.65, mx plus b. The calculator just gave me the equation of this line that best fits the data. How cool is that? So cool. Not only that, but it gave me the correlation coefficient, the linear correlation coefficient, 0.997. Great. And the only reason the definition formula is off by 1,000th is because of rounding. I rounded Doc Pfeiffer rounded these 2 numbers. Okay, so what does this paragraph say? It says what we already stated, that R is just an estimate of rho. So now let's do a hypothesis test and call it a day. All right, use the 0.05 level of significance to test the null hypothesis of no linear correlation between speed and miles per gallon for the data below. So we have L1, put that in L1, miles per gallon, put that in L2. If you want to pause the video and practice it right now, go right ahead. I encourage that. So our hypotheses, HO and H1. HO and H1 will always be the same for this test. Rho equals 0. There is no linear correlation between speed and miles per gallon. Versus rho does not equal 0. There is a linear correlation between speed and miles per gallon. Significance level alpha 0.05. As far as the test statistic, you can write either the definition formula or the computational formula, whichever floats your boat. Pick one and write it. The assumptions. It's a random sample of paired data. Okay. Then check these out. The Y populations are normally distributed at each X value. The Y populations have equal variance at each X value. And both populations are normally distributed. I made a little note in my own handwriting. This particular correlation coefficient comes with lots of baggage, meaning there's lots of stuff that needs to be met in order to do this test. So the natural question might be, what if all this stuff cannot be met? We're doing that in the next lecture. I'm glad you asked. But for right now, let's assume that all of this has been met. The decision rule, we're going to reject HO if it's a two-sided test. So if R is greater than something or if R is less than something. If R is greater than S with R is greater than R with N pairs of data. N equals the number of pairs of data. Okay, so how many pairs of data were there? We kind of went pretty quick. 1, 2, 3, 4, 5, 6, 7, 8, 9. So N equals 9 pairs of data. Okay, so it's written right there, 9 pairs of data. And then the alpha over 2 level, which is 0.025. So here's what you do. I'm going to attach this. This is the critical values of Pearson's correlation coefficient R. I call this the skinny table because it's so skinny. You're going to go down to 9 pairs of data, go to the alpha 0.05 column because it assumes it's two-tailed, and I see the devil's decision rule, 0.666. Oh my goodness. All right, so we're going to reject HO if R is greater than 0.666 or if R is less than negative 0.666. It's pretty basic. Great. Now we do our computation. I wrote skip. Just do it all on your calculator, and you'll get negative 0.906. So it's a negative correlation. There's a negative relationship between speed and miles per gallon. Okay, so negative 0.906 is definitely less than negative 0.666, or it's further negative. So we're going to reject HO, and we're going to accept the alternative H1, that there is a linear relationship or correlation between speed and miles per gallon. And then last but not least, because the R value is negative, we say that there is, and these are the 4 magic words, we say there is a significant negative linear correlation. 4 magic words. If this was positive 0.906, I would say a significant positive linear correlation. Ooh, what if you fail to reject? We fail to reject HO and accept that there is no significant linear correlation. Still 4 magic words, no significant linear correlation. Always 4 magic words. Okay, last but not least, some notes here. All this mumbo jumbo from Doc Piper basically just says that correlation does not prove cause and effect. We said in the first days of February, and when we still were in school, we will never prove cause and effect. I think it was with smoking and cancer. Okay, we will show that there's a very, very strong relationship between 2 variables, but here we will never prove cause and effect. It is valid only for linear data. Let me ask you, is there a pattern there? Certainly, it's exponential. But would a line catch that pattern? No, it would not. So R only is good for linear patterns. That's what number 2 says. Number 3 says, do not average the X's or the Y's. If you average the X's or the Y's, I'll come on cam for this, then high X's and low X's will average out. High Y's and low Y's are going to average out, and things are going to look more correlated than they might otherwise be. And last but not least, I'm going to take this. This is the most important one, as a matter of fact, and put it down here. There are 3 extremes. All right. In general, R is always going to be a decimal between -1 and +1. What will it look like at the 3 extremes? Well, what if R equals -1? What would the scatter plot look like? What if R equals +1? What would the scatter plot look like? And in between the two, what if R equals 0? What would the scatter plot look like? Well, if R equals +1, that means magically all the points are going to line up perfectly in an upward pattern. If you pick random data points, are points ever going to line up perfectly in an upward pattern? No. But if they did, R would be +1. All right. What if R equaled -1? The points would line up perfectly in a negative pattern. Is that ever probably going to happen in real life? Probably not. But the closer to that, R equals -1. R equals 0 means absolute absence of a pattern. Complete absence of a pattern, of upward or downward pattern. Will that happen in real life? Also, probably not. The moral of the story is this. The closer the points are to each other in an upward pattern, the closer R is to 1. The closer the points are to a downward pattern, closer to each other to a line, R equals -1. The more scattered about points are, the closer R is to 0. That's the takeaway from this. Last but not least, your homework's out of the book, but there is one worksheet problem, which I'll attach. Types of correlation. Positive correlation means that as one variable goes up, the other variable also goes up. It also means as one variable goes down, the other variable goes down. As long as the variable goes in the same direction, it's a positive correlation. A negative correlation means that as one variable goes up, the other variable goes down. Okay, so just point that out. An example of a negative correlation, I'll do one and then I'm going to call it a day. As the temperature in the winter goes down, your heating bill goes up. That's an example of a negative correlation. Nope. Okay, an example of a positive correlation. As the amount of time that you study increases, hopefully your grade possibly increases. That's an example of a positive correlation. All right, everybody, you got questions? Ask. There's one more hypothesis test after this I'm going to do a video for. Bye.